Okay, this is the introduction for the Revenge of the Atwoods Machine Lab, and the setup's going to look nearly identical to the Atwoods Machine Lab, except for we're going to go ahead and put a disc on the pulley that's attached to the rotary motion sensor. The picture right here kind of shows the rotary motion sensor hanging off the edge of the table. If you get one of the tall ring stands, and you don't actually need to hang it off the edge of the table. If you get one of the shorter ones, then you will need to hang it off the edge of the table. Here's what we need. We need a computer with Logger Pro. We need a string. You need about a body's length worth. Rotary motion sensor. We need the mass set and an aluminum disc set. So let me show you what these guys look like. When it comes to the mass set, we'll be using the same hanging masses that we did before. You're going to get the 50-gram hangers as well as 150 grams to total 200 grams. I highly recommend that you tape these guys on there with a little teeny tiny bit of painter's tape. And we also need some of these washers out of the Maxwell house can. Here we have the rotary motion sensor. You've played with these guys before. It has a pulley that you can attach. One thing I want to keep in mind is you're going to be measuring the radius of this pulley in just a little bit. Do not confuse that with the radii of the aluminum discs that you're going to be attaching to this pulley. If you look inside of this white box right here, there's probably a plastic bag that has 4 discs in there. What you want to do is the disc with the big hole in the center as well as the pads, you want to put that right back into the bag, and the big washer, you want to put that right back into the bag. You want to get yourself this disc, and the very first thing we're going to do is measure the mass and the radius of these discs. Actually, the very first thing you're going to do is measure the radius of the pulley, and again, please don't confuse the radius of the pulley with the radii of these discs. We do want to work with the largest pulley on this 3-stage pulley, and you want to go ahead and use the calipers to measure the radius of this pulley. When you're done, please take the battery back out because these things turn themselves back on, and it kind of kills my batteries. So that's what we're going to do first, is we're going to use the Pulley Radius, and much like the Atwoods Machine Lab, that's going to let us convert linear speed or angular speed to linear speed. Let's go ahead and measure the radius and mass of the 2 aluminum discs and record them here. And we're going to calculate the theoretical moment of inertia for these discs, or the rotational mass, if you will. Now what you're essentially going to be doing is you're going to be saying the rotational mass of disc number 1 is going to be 1/2 the mass of disc number 1, as well as the radius of disc number 1 squared. We can go ahead and calculate the radius of disc number 2 in the same way, 1/2 of the mass of disc number 2 and the radius of disc number 2 squared. And if I wanted to know for some odd reason the moment of inertia or rotational mass of both discs, I would add this rotational mass to this rotational mass. Just kind of saying. Make sure you show your work and don't forget units on this. For some reason, everyone always forgets units. Then what we're going to do is we're going to set up the Atwoods machine, and we're going to attach the disc to the pulley using the screw that's in the center of the pulley. And we're going to make sure we have about 40 centimeters before striking the floor or the table. So that's this distance h right here. You're going to plug in the rotary motion sensor, and there's a really good chance you need to say, hey, expect a rotary motion sensor. You're going to put 200 grams on one side, you're going to put 200 grams on the other side, and then you're going to go ahead and put a washer on one of the side. You do want to record the masses and the height in the data table because we're going to be using conservation of energy in just a little bit. You're going to position mass number 1 about as high as it can go and go ahead and collect some data. Now, the schematic right here is nice, but let's go ahead and take a look at what it looks like in reality. Here I've got my disc attached to the pulley, and here I've got my lower mass, and here I have my upper mass. One thing that you will probably note is look at how much space we have. I don't have 40 centimeters right here. If I were you, what I would do is I would go ahead and get this mass right here on the table, and I would go ahead and I would tie a new knot right here, and I would move this mass all the way to the top so that way I have all that range of motion to play with. Just a suggestion. Then you need to go ahead and release the heavier of the 2 masses and allow it to go all the way down and strike the table. If these masses hit themselves in the middle, then you need to redo it because we don't want to have anything external influencing the conservation of energy. So then what we're going to do is we're going to let it go all the way down. They must miss each other on the way down. And then you can use the examine tool to measure the angular speed just when the mass struck the ground. You're going to record that in the data table, and you're going to convert this thing into linear speed. How are you going to do that? Well, you're going to say, aha, now that I've seen Chapter 9, I know that linear speed is going to be equal to the radius of the pulley, not the radius of the disc, multiplied by the angular speed. Then all we're going to do is we're going to repeat these steps by increasing the mass on the heavier of the two washers, and we're going to go ahead and fill this guy out. So this is going to be 200 grams. This is going to be roughly 226. You're going to record the height. You're going to record that, and you're going to calculate that. I know that you really want to fill this thing out, but don't worry, you're going to be doing that in the calculation sections later. So then you're going to go ahead and increase the mass, and everything right here just kind of falls in place. Then all you're going to do is you're going to add the second metal disc to the pulley, and you're going to repeat the experiment. That's going to be this guy right down here. Again, you're going to start off with 200 and 226, record the height, record the angular speed, convert to linear. I know that you really want to fill this guy out, but don't worry, you're going to fill that guy out in the analysis section. Once you have all of your data, then you can actually go ahead and do the analysis section on your own if you're short on time, or you're welcome to hang out and do the lab there. You're going to identify the energy that the system had before it was released, identify the energies that it had afterwards, and you're going to go ahead and solve for the moment inertia of the disks. So what I want to see is I want to see the moment of inertia is equal to a whole bunch of stuff that's going to have the two masses, gravity, the height, velocity, and the angular velocity. Now you can use this expression right here to fill out the columns in the table. Show me one sample calculation. You don't need to show me every single calculation. So now you can go ahead and fill this guy out and fill this guy out. Then you're going to go ahead and say, well, between the 3 runs of the first setup, the moment of inertia probably didn't change. So let's go ahead and calculate the average, and then you're going to compare it with the theoretical. Then what you're going to do is you're going to do that for both setups. So you're going to do that with 1 disk and 2 disks. Remember that when we're doing 2 disks, what we can do is I can say the moment of inertia of both disks is going to be equal to the moment of inertia of disk 1 plus the moment of inertia of disk 2.